If you think MiniMax H3 produces great-looking videos, but generating them directly at high resolution takes too long, today's workflow is probably one of the most worthwhile solutions to try right now. Let's begin with the results here. We have a selfie shot inside a subway passage. The character's face is very close to the camera, yet her facial features, hair, and skin texture remain extremely clear. When she turns her head, raises her hand, and smiles, her face doesn't noticeably fall apart. Now let's look at scenes with more intense movement, riding a horse by the sea, stir-frying food in a kitchen, and even fast-moving skiing footage. The motion details are rendered more clearly as well. I also tested stylized characters and unusual low-angle shots, and the overall quality is very high. These videos weren't generated in a single sampling pass. We first generate a base video at a very low resolution, upscale it in latent space, and then perform a second refinement stage. This approach is very similar to the two-stage high-resolution sampling method we used with LightX 2.3. Pay attention to the quality of these results. We're also using the latest turbo acceleration model, together with a new attention mechanism that makes the entire workflow sample faster. So how does it all work? Let's go through it step by step. First, we need to install an extension. What you're looking at now is its GitHub page. Clone the repository directly into your custom nodes folder. It provides both two-dimensional and three-dimensional latent upscaling nodes. The two-dimensional version is lighter and faster. The three-dimensional version jointly processes spatial and temporal information, so it requires more computation, but it provides stronger overall consistency. We'll use the three-dimensional version today. Installing the node alone isn't enough. We also need to download the upscaling model. The repository provides 3 files in slightly different formats: BF16, FP16, and FP32. Their network structures are basically the same. The main difference is numerical precision. I'm using the FP16 version in this workflow. After downloading it, place the model inside the Latent Upscale Models folder under ComfyUI models. The third step is downloading the Turbo LoRa. This image-to-video workflow uses LightX2V's latest first and last frame turbo model. Version 1.1, compared with the previous version 1.0, it produces better results. However, for reference to video generation, the corresponding turbo model is still version 0.1 and hasn't received a later update. Its generation quality is slightly weaker. I also recommend updating ComfyUI to the latest version, because this workflow uses a new node called Model Attention Backend. It includes a new attention mechanism called Comfy Kitchen Attention. If your ComfyUI installation is too old, you may not find this option. For easier testing, I've also built the workflow on Running Hub. In the ComfyUI space, Running Hub is a great online working platform because whenever a new model or extension appears, it usually adds support very quickly. Running Hub also provides an online community for ComfyUI creators where you can find plenty of creative inspiration and example workflows. Now let's examine the image-to-video workflow. It can be divided into 2 main sections. The first section performs the base sampling and generates a low-resolution foundation video. This stage mainly establishes the character, composition, and movement. The second stage upscales that result and performs another round of sampling. Before this second sampling pass, we enlarge the latent, then sample and decode it. The result is a high-resolution video. Let's start with model loading. The main setup is unchanged from the official workflow we looked at previously. It still includes the main model, the QW3VL text encoder, the video VAE, and the audio VAE. The real changes happen later in the pipeline. First, we load the corresponding turbo LoRa. As I just mentioned, this is the new version 1.1 acceleration model, and its weight is set to 1.0. We then connect it to the new model attention backend node and switch the attention mechanism to Comfy Kitchen Attention. In other words, we're applying 2 layers of acceleration. The turbo model reduces the number of sampling steps, while the new attention mechanism improves computational efficiency. Next comes the first sampling stage. Let's look at the overall process. First, we need to set the base resolution. We use this node to select an aspect ratio of 16:9, then set the megapixels value to 0.2. That gives us an actual resolution of 608 by 352. You can see the corresponding calculation in this table. The first stage therefore runs at a fairly low resolution, which makes it much faster. The most important node here is still MiniMax H3 image to video. Notice that the workflow now contains two instances of this node. One is used for the first sampling stage, and the other is used for the second. Beside them is another interesting node called Model Preview Override KJ. It comes from the familiar KJ nodes extension. To use it, you need to download a small preview model commonly called T3. This preview model doesn't improve the final video quality. Instead, it allows us to preview the video before the full generation process has finished. If the character, camera, or movement direction is already clearly wrong, you can stop the job immediately instead of waiting for the entire workflow to complete. Now let's look at the sampling settings. We use Euler as the sampler and Simple as the scheduler. The complete process contains 8 sampling steps, but we use a node called split sigmas to divide them into 2 sections. During the first stage, we only use the high sigmas. This section is responsible for establishing the video's overall structure at low resolution. Once the first sampling stage is complete, we don't pass the result through VAE decode. Instead, we send it directly into the upscaling pipeline. The main node here is called MiniMax H3, Latent Upscaler, 3D. Notice that this node only processes the video portion, so we need to separate the video and audio latents beforehand. We then upscale the video latent with the 3-dimensional model. Once that's done, we merge the audio back in to create a complete latent again. The 3-dimensional upscaling node supports 3 ways of defining the output size. The first is to set a scale factor directly anywhere from 1 to 4 times. The second is to specify the target width and height. The third is to enter a target megapixel value while preserving the original aspect ratio. In today's workflow, we're setting the width and height directly. Those values are controlled by the second resolution selector, and they must be multiples of 32 pixels. For the upscaling model, we select the FP16 version. The workflow then enters the second sampling stage. This stage refines the upscaled latent. Finally, we decode it to get the finished video. As you can see, the generated result looks excellent. This method isn't limited to image to video. It also works with reference to video. Most of the workflow remains the same, sample at low resolution. Separate the video and audio latents. Upscale the video, merge them again, and perform a second sampling pass. There are 2 main differences. First, the reference input isn't a first and last frame. Instead, we use a character sheet to provide information about the character, clothing, and overall appearance. Second, you need to select the dedicated reference to video Turbo LoRa. However, you'll notice that its generation quality isn't as good as the image to video result. The main reason isn't the upscaling method, it's the acceleration LoRa itself. Its version is relatively old, so its generation quality still needs improvement. You can also disable the turbo model and sample with the full number of steps, which can produce a much higher quality video. Now that we understand the workflow, let's examine what the upscaling model actually improves. I've divided the tests into 3 categories. The first category is facial detail. In close-up shots, the eyes, lips, individual strands of hair, and layers of skin texture remain very complete. The value of upscaling becomes even more noticeable when the character occupies a smaller portion of the frame. In the original low-resolution video, relatively few pixels are allocated to the face. After increasing the final resolution, the facial features, hair, and clothing edges of a medium-shot character can be represented much more clearly. The second category is motion detail. In the horseback riding scene by the sea, the horse's running motion, the rider's vertical body movement, the direction of the clothing and hair, and the falling water spray are all rendered very well. In the kitchen scene, the relationship between the pan, the stir-frying movement, and the moving steam remains very stable. The motion also looks natural. With skiing, fast movement, and more complex character actions, the model doesn't simply make the image sharper. It brings out the snow mist, clothing, hair, body contours, and depth in the background, then refines them further during the second stage. This is the most visible difference between learned latent upscaling and ordinary pixel stretching. The third category is adaptability to visual styles and camera angles. Stylized characters can preserve a consistent visual language after upscaling. even in night scenes containing reflections on water and glowing elements. In shots with unusual camera positions, the character's face, fingers, phone, clothing edges, and the structure of the train carriage also remain relatively stable. Based on these tests, this method isn't limited to standard half-body portraits. It also adapts well to close-ups, medium shots, fast action, vertical videos, stylized scenes, and unusual viewpoints. To sum it up, the core idea behind MiniMax H3 Latent Upscaler is simple. Establish the structure at low resolution, then refine it at high resolution. The first stage uses very few pixels, so sampling is fast. When we combine that with the Turbo version 1.1 acceleration model and the new Comfy Kitchen attention mechanism, we can balance image quality and efficiency inside a single workflow. But remember, the main purpose of this workflow is to save time, not VRAM. Personally, I think it's a very worthwhile workflow to explore, and I hope you'll try it for yourself. That's all for today. Follow me and become someone who truly understands AI.